Thank you, Raja. You can hear me back. All right. All right. I'm pleased to be here, and it's good to see familiar faces on the TV there. So, welcome, everybody. With me, my good friend Raj is here. So, between the two of us, we'll be happy to answer any questions. So, usually I make the title of the presentation Key Challenges in Aeronautics Enterprise. But since I am with you all, more intellectual people. I'm looking that as an opportunity for you all. Towards the end, I'll talk about how to get engaged with us as well. Let's see if this works. All right. So quickly, for those who know me, as Raja introduced me, I usually start with airspace operations, but today I'm going to do something different. I'm going to start with the future of aircraft and go from there and then talk more about the airspace towards the end. A lot of people have already heard me talking about airspace. So I'm going to start talking about aircraft first. So we'll cover the aircraft, the needs for the aircraft design and what challenges exist today. And then we talk about the operations of the aircraft as well as the airspace system at large. So if we look at the aircraft, what's happened, nothing has changed ever since you were born and started taking your first flight. Right now, you start to see some new models emerging. They're still in the development stages. You have the blended body wing, which is supposed to reduce fuel consumption. You have electric propulsion that's emerging. You have supersonic that's coming back, which will have a sonic boom that's much more acceptable. And then you have electric vertical takeoff and landing vehicles. So these aircraft are likely to be in existence from 10 years from now, with significant impact to going farther and faster with supersonic over land. That's one of the big challenges. How do you go with supersonic over the land without interfering due to the sonic boom? And then going closer and closer towards urban and suburban areas with electric propulsion, with vertical takeoff and landing. So those are the two extremes that you're seeing. One is faster and farther, and other one is getting into regional hubs and closer to your basically neighborhoods. How do you enable all of that? And there are significant challenges with both types of aircraft. So let's look at the more electrified aircraft. It is the right thing to do from many reasons, not the least for climate change and such, but more electrified aircraft for reduced emissions has been the goal for a while. There's a significant amount of development going on towards hybrid electric propulsion as well as more electrification. The challenge still remains about the battery needs for aviation. So that's one significant area where we need you all to basically pull resources, ideas, see what kind of propulsion, electric propulsion technology we can use to be safer. Thermal runaway problems still exist, what most people like to just call explosions, but fancy term, we still haven't solved that problem to our satisfaction where we can carry people. So that's one problem. Second problem we have is reduced aircraft development cycle time. So if you look at every modern aircraft, if you look at 777, 787, and 380, 320, all aircraft were delayed by a decade almost from their inception or the planned date of entry. Over budget by billions of dollars and heavier than originally anticipated. People are not the only ones who worry about the weight. The aircraft industry really significantly worries about the weight also. All aircraft, these new entrants, have been shown to be delayed, over budget, and overweight. And that's got to change if we really want to transform the industry. So the design complexity is very, very high. I know Berkeley is interested in getting into aerospace. Anything you can do to change the design complexity will significantly improve the potential for entry of these vehicles. If you just take an example of Airbus 380-800, which has over 100,000 wires, 470 kilometers of wiring, with 5 tons of weight of wire, and then another 30% weight on the harness. Every ton costs a lot of money in operation. And the goal is to try to, how can you reduce the weight? How can we simplify the architecture of the aircraft and the design itself so that the modern aircraft can enter faster much more lighter and much more economical. That's a challenge. If you look at the production rate and supply chain, we'll talk about the production rate and then we'll talk about supply chain in the next slide. Production rate, the current production rate is such that there is an $800 billion worth of backlog. That's 800 billion B. Boeing and Airbus produces about 50 aircraft a month. Airbus just started producing 56 or so, I think, or close to 60 aircraft 2019. They produced 860 aircraft last year, but usually 800-ish. That's the production rate. And there are 4,000 aircraft behind, 5,000, 4,000 aircraft behind back order. That's a significant impact to our economy, and that's got to change. What can we do to improve the rate of production of these vehicles? As I said, Airbus produced 863 last year, and I skipped the last year for Boeing because of the MAX situation, but Boeing had 5,000 undelivered orders, and Airbus has over 6,500. So that's what we are looking at. We have to figure out how to change this. If we don't solve this problem, aviation growth is going to be limited. Let's look at the supply chain. Because the supply chain is so brittle in aerospace, a lot of companies, Boeing and Airbus, they did vertical integration. I know you've taken courses in business and such, so you know the challenges and advantages of vertical integration. Vertical integration has one big problem, which is innovation doesn't happen at all fronts. There are significant challenges related to the casting, forging, composites, power units, circuit boards. There are some companies who can't get circuit boards inside the United States. They have to go outside US. And if there are military, they have restrictions on using circuit PSCBs from certain countries. Another funny example of this supply chain problem is Airbus deliveries were delayed because they didn't have enough business class lavatories. They couldn't produce. That's not a problem I ever experienced because I don't fly business class. But and I said I don't care if they don't. But the reality is that kind of stuff should not happen, right? So supply chain is a big problem in aerospace industry. It's a very brittle supply network. But the reason I'm telling you this is there are huge opportunities for folks like you to start new businesses related to focused areas in the supply chain of this aerospace industry, where you can actually include the technology pieces, your business acumen, figure out where the new areas are going, and launch new businesses to accelerate the production rate and supply network. Other part is the maintenance, repair, and overhaul. That's another multi-billion-dollar industry, and the huge opportunities there. It's not as lucrative in terms of telling everybody I'm doing maintenance work, but really is lucrative business if you look at it. Every organization needs MRO, and as you start going towards electric vertical takeoff and landing vehicles, urban air mobility, we were just talking with Raja before, what are the challenges? Think about it. When you have a car that breaks down, you go to a garage. I don't go to the dealer. I'm too frugal. I'm not Google, so I go to the local garage, say, hey, get my part fixed. They look into the computer database, get the part from somewhere. There's a supplier network available. If you're going to have urban air mobility, electric vertical takeoff landing operations, you're going to need a significant supplier network at each region that is allowing these operations. Another huge business and opportunity that exists to set up the supplier network and support MROs. It will also require maintenance technicians and a whole bit that are aviation grade and certified to support that. So try to break that logjam of supplier network and MRO. What's happening is car companies are entering into the aerospace. They think that they have the ability to mass produce the cars, so they have ability to mass produce aerospace parts. And to some extent, that's true. But aviation manufacturing and production certification is a different ballgame than just manufacturing parts. So you really need to understand the production certification process from regulatory authorities, whichever country you want to operate, and then manufacture aviation grade parts. Now, there is a body of research that you can actually do here to identify and compare the levels of parts and the types of impact and the fatigue properties and material structures and all of that to say, where can I actually reformulate these materials based on the experiences I had with heavy industry and auto industry, and which ones will be applicable for aerospace. So you don't have to always use carbon fiber, which is nice and light, but very expensive. Another challenge we have in the aerospace industry is when you're starting new product, new kind of design prototype, you try to go to a company and say, I need ball bearing. And they say, well, great. How many do you need? How many thousand can I ship you? They said, no, I only need 4. They said, all right, then take a number, because I'm busy dealing with Boeing and Airbus and a whole bunch of other people. And they want thousands, and you want only 4. So how do you actually break that logjam and create ecosystem where you can turn around suppliers fast enough for the early stages? So again, summary of that is cycle time for aircraft design from drawing board to actually inception is very important, and production rate is very important. That includes everything: materials, actuators, avionics, bathrooms, whatever have you, seat belt. All of those need to be rethought through. How do you actually use different materials? Maybe some computational analysis, maybe some lessons learned from historical data to say, what can I use for aviation grade parts? What kind of materials would be better? Can I create new materials altogether based on the needs of the future? Now so that was all about aircraft. Now I'll transition to the airspace operations. So this is where Mark has done many studies. So he's got a lot of papers and understanding of the airspace system as well. But increasing efficiency of current airspace operations is really key here. So we can use a lot of data, historical data, to understand the inefficiencies in the system. Here's a good example. A few years ago, FAA changed the rule and said, you are not going to be considered delayed if you are within 15-minute block. So a lot of companies were getting penalized for being delayed, so they all added buffers. So how many of you have taken flights very recently and got early and waiting for gate? How many of you have done that? Yeah. So many of you have realized that experience, had that experience. That basically tells you that the system is extremely inefficient. They have padded the flight durations so that they won't be considered late. Now you're paying for pilot, you're paying for flight attendant, you're paying for all those things in aircraft block time when you should not have to pay for that. The system could have been a lot more predictable and said, why am I paying for 25 minutes of extra time on every flight? That just does not make sense. So here's where we can use a lot of historical data and say, let's get rid of the padding. We don't need that padding. Maybe the regulation needs to be changed. I'm not worried about 15-minute block delay. So lots of inefficiencies that have occurred because of these things that should be relooked at it and redeveloped. The second example is automation for reducing the impact of disruption. So about 25% aircraft get delayed in the system. Out of those, about 70%, 60 to 70% are due to weather. And major disruptions, you can see the volcanic ash, typhoons, 9/11, lots of those. I've been on every one of those major disruptions. On 9/11, I was flying from Philadelphia to Los Angeles for actually collecting data related to the complexity experiment that Raja was mentioning. I got stuck in Kansas City for 5 days. I was flying, so that was, then the next experience I had, volcanic ash. That one, we were flying back, we were supposed to fly back from Amsterdam to San Francisco. Got stuck at a little better place in Amsterdam for 5 days while waiting for airspace to be open. I've been stuck at Hong Kong airport for about 22 hours because of the typhoon. All of these, while you can't do anything about those extreme events, so you're shut down. But there are, in between, there's a huge opportunity to say, how can you actually learn from what has happened in these delay profiles, and whether the delays were excessive? Could we have rerouted aircraft in a different manner, and could we have done something different? So deciphering this every day, all day, on a continuous basis is really needed. And you can actually look at the previous data. There are flights that come from Europe to East Coast every day. Sometimes they're 45 minutes early. They're early because of good winds. Now, you could have predicted the winds. You had the trajectories. You could have figured it out that they will come early. But instead, they come early. And they're either spinning at the New York area or waiting for the gate to open at the airport. None of those are desirable. And so here we can actually use some data-driven approaches and historical basis. The other one is figuring out avoidable and unavoidable delays. So San Francisco, how many of you got delayed coming in San Francisco? So yeah, so you've seen that happen because there is a marine stratus. A simple term for that is fog problem. A certain time of the year, out of between the two runways, if you don't have clear, basically visibility, the rule says that the procedure requires that the trailing pilot has to be able to see the aircraft, lead aircraft, so that they can land parallel to each other. Have you seen the parallel runways and approaches? So those are really beautiful to watch. If you haven't seen it, go to Embassy Suites parking lot in Burlingame. It's really beautiful to watch that all day, every day. It's really fun. But if you haven't seen that, go take a look at it. But regardless, what happens is when there is a fog, because the trailing aircraft pilot cannot see the lead aircraft, they shut down one runway. Only one runway is open. Arrival rate from 65 per hour drops down to 35 per hour. Now, this problem you can fix. We can fix this by better electronic means. Right now, the procedure is visual. But if you couple the FMSs between the two, and the reason that is there is because of the blundering. So what happens if the aircraft in the front blunders or drifts, then the pilot, the trailing pilot has a fighting chance to move around. That's why the procedure exists. But you can do that. You can fix that by coupling FMS, and you can fix that by electronic exchanges of intent information real time. So there are many ways to do that. The other thing we can also do is use probabilistic data methods that say, we know from historical data the time at which the fog burns off. Use that information to populate your departure times from Chicago and New York and Washington so that you will get there at roughly about the time where the fog will be burning off, around 11:30, 12:30 in the morning. So you can use some historical data and learning algorithms to try to predict the fog burn-off times and then use that on a daily basis, as well as technology solutions to couple these things on FMS particularly and reduce the avoidable delays. So that's what I mean by better automation. In terms of safety, we have a great database. NASA has developed this for decades now. Aviation Safety Recording System, ASRS, where you will see lots of interesting incidences and pilot recordings as well as controllers. And you will be able to extract those and figure out what's happened, why are there incidences, and make a systematic analysis from that to figure out what can you do better about it. And then that also applies for future aircraft and future transportation, such as vertical takeoff and landing vehicles and urban air mobility and all of them. You can also look at operational errors, which is where controllers are operating the two aircraft and they get too close to it. And this is a line I took from one of the controller performance-related papers that says every hour around here is 59 minutes of boredom and 1 minute of sheer terror. If you haven't, I don't know how many of you have gone and seen the air traffic controller system in operation, but if you haven't, I would highly recommend you go watch it. You will realize that a lot of times they're bored, but there are times when they really get tight in terms of trying to and get overloaded, and then the second person and third person sometimes work together as a team to solve that. But operational errors, which is when the aircraft get too close to each other than required, so en route airspace is 5 miles. When that happens, why did that happen? To learn from the historical data, figure out how to avoid that for future. Pilot deviations is when Pilot is given one altitude, but they misunderstand it and go to a different altitude. So that's another error that's common. See, these two things, you can actually learn a lot from what's happened in the history. There's a nice report that was produced on operational errors a while back. So that report is pretty old, but since then, number of new technologies have been inserted, and this kind of look needs to happen again one more time to figure out what causes the operational errors in the context of new technology, particularly. The other area that is very interesting, which is the confluence of technology and humans. It's almost causing divergence of human capabilities and technology. In the past, when aviation started, aircraft stage length was limiting factor. Now it's opposite. Stage length, you can see in this chart here, 18 hours, 17 hours, 16 hours. They can go on and on and on. Long, very, very long flights. But fatigue rule has become more conservative. So a few years ago, fatigue rule said that if you're starting between midnight to 5 o'clock in the morning, your duty time should be only no more than 8 hours. Think about what that means. You have 18-hour flight and your duty is only 8 hours. So they are basically carrying 2 more crews on flight who are sleeping. There's no other job where you get paid to sleep, right? So this is what happens. And then if your turnaround time is very small, if you're going cargo Tokyo and then come back, load it in 3 hours, 2 hours and come back, they don't have enough rest and they had to come back. When you had to come back, you had to carry another set of crews. That increases the cost of transportation significantly. So this is an interesting problem of where the regulation based on fatigue is now limiting the stage length or increasing the cost because you had to carry multiple crews. How can we change that? So let's look at one option. So someone can argue then that let's just train more pilots. The pilot shortage is coming, and so let's train more people. Pay them more. Is that practical? We don't know. Because there's another country is coming in the market. They might have aircraft that's going to be significantly cheaper, possibly cheaper to operate. So how do you compete with that? Is just training more people as pilots is a solution? Or is it really about increased autonomy? Instead of training pilots, you can say, why don't I go from 2 pilot operation to 1 pilot operation? Or at least when I'm going on a long stage length using cargo or people, instead of carrying 3 sets of crews, I'll carry only 2 crews, reduce 1 set of crew and say, on takeoff and landing, I will have 2 pilots, and only crews, I will have 1 pilot, and change that. So there are a number of options available for us to sort of conduct research and say, what's the right thing to do from efficiency perspective, from economics perspective, but also from safety perspective. What would you want to do here? What is the paradigm that we need to go towards? So is it really time for now increased autonomy where we can get away with saying that let's do fully autonomous aircraft? Is that practical? What would it take to get that accepted? We don't know. So this is another area of rich area of research where you can contribute to significant body of knowledge to try to change that. Here you will see some of these quotes, Boeing CEO says, global pilot shortage and things like that. So now let's talk about how let's assume that we are successful in all the things I said. You guys are smart, you solve the problem of production rate, you solve the problem of battery, all of a sudden we got lots of aircraft coming into airspace. How are we going to do that? How are we going to manage all of these in the airspace? When today's aircraft operations are 50,000 per day, sorry. One operation is takeoff or landing. Now we're talking about millions of these operations. How are we going to enable air traffic management system, which is based on pilot and controller communications, and every change that happens today has to be approved by air traffic controller. So pilot cannot do anything in terms of changing altitude or speed or direction without controller's approval. Maybe just going to the bathroom is all they can do by themselves. But this is a tricky thing. So how do you actually change that paradigm from clearance-based to something different that allows us to scale these operations? The reason it doesn't scale is because controller is the only entity that has all the information about all the traffic. They're watching and they're separating them, these flights, as well as contacting and talking to the pilots. So they are the bottleneck. Their workload is the limiting factor of the capacity of en route airspace. So how do you fix that? At the same time, we have new entrants coming in, and they want faster access to the airspace. So drones, commercial space, balloons, all of these new entrants are saying, hey, I want access to the airspace, and I want to go now. So airspace system as a whole needs to be ready when the vehicles are ready, right? Today's paradigm is vehicles get ready, they come and say, I want to fly, get me ready, get me access to the airspace, and then we tinker with the regulations and such and try to figure out how to get them in the airspace. That paradigm needs to change. We need to bring and put together an airspace system and architecture such that it's scalable for future. So new entrant, whoever is that happens to be, we can just plug them in. So we started this with something called unmanned aircraft system traffic management for drones. And this was ideal because it's classical disruption where we focused on 4,000 feet and below. We focused on uncontrolled airspace where typically nobody provides services. It was small enough to start with, manageable. You know, in classical Silicon Valley terms, it's MVP, and in Clayton Christensen's book, it would be categorized as disruptive innovation. So what did we do? As I said, the current paradigm for air traffic management is based on clearances and delivery of clearance between controller to pilots. We changed that paradigm. We said we don't need to have clearances. What we only need to have is directives about airspace. And say ANSP, which is Air Navigation Service Provider, FAA in the United States, can actually say, here is the place where you can go or cannot go. That's all. The rest of the stuff is done by service-oriented architecture, enabled by service-oriented architecture with an entity we call US service suppliers, so drone service suppliers. They can plan trajectories or areas of operation. They can track, monitor. They can do all those things by themselves and interact with each other by prescribed data exchange protocols that we build. Now, big companies like Amazon, Google, they would be the operators as well as service suppliers. But smaller entities like real estate and whatnot, they can get services from outside. So this model now has been tested through many iterations, and we are seeing its inception already at the global level. So this is the way we changed the paradigm from clearance-based air traffic management to managed by exception-based air traffic management. So this allowed us to scale these operations, and heart of that, basically there are 6 main properties. One is service-oriented architecture. So instead of one entity providing all services, we broke that and said architecture allows to have multiple entities provide services. Third parties can provide those services. They are cooperative, so the operators will interact with each other in real time, which is not what happens today. Then everything is digital. There is no voice communication. There is no central authority. It's all federated. They interact with each other through digital means. They share intent. So they share and care about each other in the airspace because they are aware of each other's location and intent, which is what doesn't happen to them. And it goes towards managed by exception rather than managed by clearances. Just tell me what not to do. And then I will take care of what is good for my business objectives. I will plan and follow my own trajectory. That's the new paradigm. Of course, anything in aviation, you have to demonstrate and you have to make sure that it's safe. So we broke this into 4 capability levels. First one was to validate this cloud-based architecture. Second is to use this architecture, exchange information among operators with predefined protocols with third-party services. And then The third capability level was to add detect and avoid in presence of manned aviation. So the first two focus only on drone to drone. Third one included the drones and manned aviation. And fourth one, we tested this concept in tight city corridors, Reno and Corpus Christi. Never been done before. This is the first time drones flew, multiple simultaneous drones flew in large city centers. Never done before. That allowed us to show what can be done through this kind of architecture and the new paradigm that we built. And drones is a great example because it's relatively low risk, even though there are risks associated with that, flying over populated areas, but relatively low risk. But that gave us enough confidence to expand the paradigm of the UTM, which is the cooperative traffic management with managed by exception type paradigm, towards other airspace. So we are now exploring the use of UTM type construct for enabling urban air mobility. The reason we are doing that is similar, which is urban air mobility postulates multiple vehicles operating in the sky at the same time. And if you want that to happen, you can't overload air traffic control system. Again, the same problems that I mentioned, air traffic controllers workload should not be the bottleneck. So you need to have awareness to the air traffic management system. You need to show who is all operating, where they're operating, but not be limited by the human workload. So we are also working on enabling urban air mobility through this kind of a construct. Then you add the layer to urban air mobility vehicles, large drones, and the people carrying and cargo carrying larger vehicles will interoperate in the same airspace. Then we definitely need to make sure that they are connected, digitally exchanging information about each other's intent, as well as we have a system in place that allows to broadcast any restrictions or directives. President is in town, everybody needs to clear the airspace. All those things can be done through that system. Search and rescue operation is planned, everybody needs to vacate the airspace. That information can go to everybody. So fast forward that and say, how do we actually start to take that idea of scaling airspace operations with digitally connected cooperative traffic management? How do we do that for entire airspace? So we divided up. As I said, we started here at 400 feet. We're also working on urban air mobility. There are a few other things that happen in urban air mobility, like vertiport scheduling and spacing and sequencing. So there's more work there. Then we are also trying that for high altitude UTM, which is upper East, 60,000 feet and up, which is where the Google Loon and larger high endurance, basically drones will operate there, as well as supersonic. We are also working on space traffic management, which is above Kármán line for LEOs. And slowly, we are going to try to change the conventional manned aviation, class A, B, C, D, going towards service-oriented architecture. So digitize it, create new services, and allow the third parties to offer these services and interact with each other. Fundamentally, it's cooperative, it's intent sharing, it's digital, it's standardized protocols that allow us to talk to each other. They are air-ground integrated, use a service-oriented architecture with third parties. There are now still more interesting problems to be solved. So I have a paper that will come out in ATCA journal pretty soon here, but one of the things that I said in that paper is, right now we have visual flight rules and we have instrument meteorological condition-based flight rules, IMC and VMC conditions, which is visual meteorological conditions. Those are based on prior technologies and prior ways of operating. In a digitally connected world, if everybody is connected to each other, every aircraft can have access to information about the other aircraft. Do we need those rules? Why are we bound by the VMC, IMC, VFR, IFR rules? Can we change the paradigm completely towards something totally new? That's another strong body of research that's looking forward to be done. Okay. How much time do I have? Then moving forward to the completely new airspace operations. So the way we look at the current ATM, the traffic management, is all services are provided by FAA. Human addresses all off-nominal conditions by and large to ensure the safety. Very little interaction occurs among users. There are now collaborative decision-making groups and such, but very little interaction real time during the day, during the traffic happens with third parties. Human is the primary information integrator in the system, particularly air traffic controllers. Every data about every aircraft goes through FAA systems, and its management happens through clearances. Every change has to be approved or cleared by air traffic controller. That's today's paradigm, and that's where we get limited by the workload. You fast forward to new paradigm, one we call UTM-inspired ATM, unmanned aircraft system traffic management, and it's basically feasibility towards applying to the entire airspace. How do we go about doing that? So we want to look at services that are provided by FAA and third parties. So there is a rich body of work as to figure out what are those services, what's that architecture, how do you exchange the data, roles, responsibilities, automation. If you want to scale these operations, automation needs to start addressing the off-nominal conditions. Humans are there to maintain the safety. And as long as you have humans, you are going to be limited by their workload limitations. So that scaling will always be limited by the workload limitations. If you want to be basically unattached to those limitations, then you have to have automation that will address off-nominal conditions, that will ensure the safety of operations. So automation and autonomy has to be so good that it can handle all cases to enable the safety and scalability. That's a whole new body of work that needs to be done to figure out what does that automation look like, and how do you collaborate among users for preferences and such. And that's more data exchange, standard protocols and such. But automation needs to be the information integrator, not the human. Because when human is the information integrator, then you are again limited by the workload and the processing, cognitive processing capabilities. So new paradigm towards digital, more connected ecosystem, more outside applications, and movement towards management by exception. A lot of research. There's a lot of opportunity for you all to contribute towards figuring out what is the right architecture, what is the right data exchanges, what kind of businesses should provide these services, what is their performance requirements for airspace system, as well as aircraft. How do you manage these contingencies, and then certification and acceptance methods for highly automated systems as well as autonomy. So as I mentioned, there are many, many opportunities for you all to contribute. Some of them are based on historical data, some of them are based on vision and new concepts and new technologies. And I'll stop here, and this is my last slide for public service announcements. So we have internship at NASA. So if you are interested, go to intern.nasa.gov. The one project that I am personally involved is called short-term drone for search and rescue. You can take a look at that. There are many other projects on there too. You can apply to those. You must be 16. I think most of you in this room will qualify that. So that's good enough. And then the working group, we have urban air mobility related working groups. And you can go to that website, nari.org, and you can participate based on your ideas, your concepts, your technologies, and your algorithms. And these working groups have 3 categories. There's ecosystem-wide working group for urban air mobility, but aircraft, airspace, infrastructure, as well as community. So how do you make sure that the standards are ready, requirements are ready, so people can build stuff? So a lot of times venture capitalists come to me and say, hey, PK, I want to invest in this company that is building vertiports. Should I do that? And while I can't really say spend your money on concrete or not, but all we can say is, do you know the requirements? Do you know why they're building that? Is the concrete, how big the landing pad should be, what kind of vehicle they are supposed to be landing there. Is it 5 passenger, 1 passenger? What's the wingspan? And what's the loading and how deep the concrete should be and all that. If you don't have requirements, you're literally spending money on something that you shouldn't. So a lot of these working groups will collectively work together to identify requirements and something we call Book of Requirements and Guide, BORG. And that's going to be a sort of industry level standard and keeping scorecard of the progress of the industry towards urban air mobility and advanced air mobility. So if you are interested, please join those groups. And this is my last slide. Send me your questions, email, if you want to know more about this or have any other thoughts. But fundamentally, we really need to keep embracing innovation in aviation to enable the faster aircraft design, delivery, faster, new type of aircraft, as well as scaled airspace operations. At the same time, we have to continue to respect the safety tradition that we all enjoy in aviation. Thank you. Questions?
I was just wondering if there's like a break-even point of sorts after which it's no longer really advantageous to implement something like a UTM system. So if you have an airspace that's not so busy in terms of complexity or cost of having something like that in that airspace, is there a point after which it no longer really makes sense to add a UTM system into that airspace?
So that's a valid question. Those are the kind of questions we were asked early stages when we were doing UTM. And let me take you back to 1956. Grant, are you familiar with why the air traffic management started? So I'll tell you a little incident. So 2 aircraft collided over Grand Canyon, and that started the whole air traffic management in 1956. FAA was born in 1958. NASA was born in 1958 as well. But that's what happened. It takes only 2. And actually, I would even say it only takes 1, because now if you look at UTM, the heart of UTM is not just that particular vehicle, but the surrounding. So if you want to know where can I go, where can I not go, how do you, so geofence areas over, let's say, City Hall of Berkeley and White House and all those information, bad weather, you still need to have awareness of the constraints that you need to keep away, even if you are the only flight in the sky. So how do you get that information? So if you're not connected digitally, then you have no idea what's going on, what's current. Information changes, weather changes, new constraints pop up, all that stuff gets integrated into the UTM. That's the elegance of UTM. That's why even if you're the only one in the sky, you would still need traffic management. Because you're not only separating yourself from other vehicles, but you're also separating from other constraints that are dynamic in real time. Thank you. Next question.
Hi, PK. Can you comment on the economics of these third-party providers? How do they make money? What pushes them to sort of not prioritize Amazon, maybe over the mom and pop, et cetera? How does that work out?
Well, yeah, I don't. I'm not an economist. But, and I didn't stay in Holiday Inn Express, and I didn't read Wikipedia yesterday either. But all I can say is the way it's supposed to work is, if you are a large company with fleet, then you are more likely to have your own service supplier, because that's where you save the money. You need to have your fleet planning and all the resource planning. But if you are individual operator and your flights only every now and then, you don't need to have your own USS, UTM. You can actually subscribe and pay fee for that particular flight. Now, these companies, the business models are, I will be the first one to say, these business models are still evolving. There are about 12 companies that have been approved, I think 11 or 13, maybe 13, have been approved by FAA to be the USS. And 1/3 to 1/4 of them are supplying for their own, and there are others that are supplying to to individual operators, and about 1/3 are trying to be in other than US, where they are trying to lump all these services and bundle them and offer as a government side or a big, large third-party entity for all of them. So those business models are still evolving, I would say. Yes, Mark. Yeah, you.
Thanks. On the same general theme about this multi-service provider concept, I assume these service providers are using the same airspace. They're sharing airspace.
Yes.
So, if two providers both want to use the same piece of that airspace at the same time, who decides who gets to use it?
Yeah. So the rules of priority are known, right? So those who file the flight plan first has priority, right? So this sort of, it's going to be very unlikely that both of them at every fraction of second starting the plan on top of each other. But if the time sequence is what dictates first come, first serve is what will happen, like today. And if you are right, and then they both plan at the same time or overlapping on each other, that's something that may have to be just a coin toss or something. Those things will need to be sorted out. Just like air traffic controller says, hey, I'm going to get Delta today and tomorrow United. So it maybe have to be algorithm proof that says nobody can plan the second override on that.
So, yeah, I was just wondering, so what exactly about the UTM architecture breaks the scale bottleneck?
Well, they're fundamentally not relying on a centralized entity breaks and not having human involved. It's all digital. And it's not one entity approving, the human entity approving everybody's operation. It's now many-to-many relationship. And all entities have the same information about the constraints in the airspace, which don't exist today. Only air traffic controller has that information. So now every time you need to do something, you have to go ask them, like, hey, can I do this? Because only air traffic controller knows where everybody else is. So I cannot go right because I don't know who is on my right side, particularly in the instrument meteorological conditions. In the visual meteorological conditions, yeah, you can see someone on the right or in front of you, but in the IMC conditions, you can't. So that's why you go back to this one entity that has all the information. Now we basically federated it. That information is available to everybody. So you see the constraints, and it's like driving car. Now you know, you don't have to call someone and say, can I change my lane, because I see who's there. Same logic, basically.
As you mentioned, in the future, air traffic management only manage exceptional traffics. And what are the responsibilities of the air traffic management in the future? And is there a transition paradigm or transition stage between complete air traffic control to free flight? Thank you.
Let me just make sure I understand your question. You're saying, what are the responsibilities of air traffic management in the future? And then when is the transition happens to the new way of doing things? Is that your question? So the first answer to your first question is ATC is still responsible, or air traffic management is still responsible for providing constraints into that. As I mentioned, if precedent is in town or there is a search and rescue, high priority operation, public safety operation, and that needs to occur, and everybody needs to, commerce needs to take a back seat for security reasons or search and rescue reasons, then that's one thing. They will put out directives. The system will also get any flyaway information or any deviations that happen in the drone. The drones are known to get rogue every now and then. Compass setting gets messed up, and all of a sudden they become flyaway. So if they start to get too close to the manned aviation, then ATC has a responsibility to keep the manned aviation away from the rogue drones. When will that happen? Part of the question, I think, is regulatory, and part of the question is operations. So it's already beginning to happen. FAA has already implemented the USS concept and the first steps of UTM through something called LANC, which is the Low Altitude Authorization Notification Capability, LAANC. With that, they have a static information that they provide to the operators, and operators can take that information and plan their operations in the airspace that they are authorized. So that's the first step of UTM. We have also done UTM Pilot Project 1 with FAA and number of industry members, and now that's shown successfully that we can actually do this interaction, and people and entities can interact with each other through these data exchange protocols. Second UTM pilot project required by Congress is going to happen again, starting soon this year, which will demonstrate the remote ID and beyond visual line of sight type of capabilities. Once those pilot projects are done, then it will get into the regulatory processes. So FAA has issued something called ANPRM, which is Advanced Notice of Proposed Rulemaking. In that, they have asked for comments about the UTM and how best to implement UTM. And after those comments are done in the regulatory processes, then it goes to NPRM, which is Notice to Proposed Rulemaking. So the rules are then outlined, and companies and entities and public can provide information about and their opinions about those, and then they become the rules, and then it becomes operationalized process. So that's kind of how the system is set up to go through these rule-making steps. Question?
Doctor?
Yes.
I have a question. So you said in UTM there's a decentralized with additional third party, right? How would you ensure the third party while be certified correctly, they'll be able to do their job correctly as in the same level as the current air traffic controls?
Yeah, that's a good question. So one of the things about the leveraging third parties and their capabilities is to making sure that the performance requirements are published, and the third parties are basically go through a onboarding process. So for the LANC capability, FAA has a very strict onboarding process where these USS or companies that want to offer US, they go through this inception and onboarding process, and they get acceptance of that. They had to go through certain test cases, demonstrate that their capabilities and the performance meet the requirements of the USS.
Thanks, PK. Thank you.